Hello everyone, good afternoon. We will get it started. This is the CEDAR room for track G12. It's my privilege to introduce the first speaker of this session, Adam Janovský from Masaryk University. And please read his CV on the conference website. I'm not going to take too much of his time from his presentation. Let's give him a warm welcome.
Right, thank you very much for a warm introduction. I would also like to thank the OpenSSL Foundation for having me here. I'll just try to fire up my slides, and with that being said, I think that we can start it. So my name is Adam. I would like to talk here for the next 25 minutes or so about our journey, how we've been through analyzing the publicly available artifacts that accompany FIPS 140 security certification. We also did that for common criteria, but I'll be focusing on FIPS today. And this has been a joint work with some of my colleagues. We come from Europe, from Czech Republic, from the Center for Research on Cryptography and Security. And originally, we are vulnerability researchers, pretty much. So I stand here not as an expert in certification. I believe that you are much more knowledgeable in this area than me. So take it as a slight disclaimer. But we, as a vulnerability researchers, repeatedly face a problem. Back in 2017, my colleagues discovered a critical flaw in Infineon chips that allowed them to factorize RSA keys. It was nicknamed ROCA, this attack. It was a pretty big thing at then. But at that time, they couldn't really comprehend how many, if any, certified devices got affected by this flaw. And this is a re-emerging theme that surfaces every time when a vulnerability researcher discovers some major flaw, right? You discover a flaw and then you have to assess its impact. How many devices does it affect? Does it affect any certified devices under FIPS 140 or common criteria? And so the more the better, of course, if you're a vulnerability researcher, because the more the community talks about it, the worse, of course, for the practical state of affairs. And so back in that time, the only approach that we could think of was just Googling and searching for any devices that we could find with the chip that was affected and checking whether these were actually certified or not. But we thought that there must be a better way. So we conceived a tool, open source tool, which we call SecCert. It's also available online, so I definitely invite you to check it out after the presentation. And this was our response to this problem, but we also managed to solve another problems on the way, I believe. So before talking about how it works in the backstage, I just wanted to give you a brief showcase. Basically, it's a web portal that allows you to browse any certified module. You can view information about the module. For example, its name, whether it's active, some brief description, basically stuff that you can also read on the NIST website, right? It's nothing really fancy. You could also download the security policy PDF, but we also compiled a list of like 500, 600 regular expressions that we try to match in the certification documents. So we retrieve which cryptographic algorithms are involved in the certified module and much more. And seemingly, these documents should be static, but we also figure out in the process that they change from time to time. Someone re-uploads a new PDF. It happens more with common criteria than in FIPS. But basically, when you rely on the NIST website, once the document gets replaced, you never get to access the older version anymore, right? And there could be some important information there. So we're also keep track of all the changes that happen to these documents. And seemingly, the most popular feature of our tool is a full text search over all the documents that accompany all the public artifacts that accompany the certification. So you can use it also to mine for some suspicious phrases. For example, you could be interested in searching for some hard-coded keys in the module. And there are some certified modules that have their keys hard-coded. It's not on its own a sign of a vulnerability, of course, but it could be a starting point for an interesting research. In fact, there was a recent attack on YubiKey tokens. I'm not sure if you're familiar with that. And the guy that discovered the side channel attack on the YubiKeys was facing the same issue as we did back in 2017. He was trying to figure out if there are any certified devices affected. Luckily, he got SecCert, so he could browse through our web, and check, yes, there are common criteria certified devices affected by this vulnerability. So I just want to give a very short introduction about how we do it in the backstage. Then I'm going to talk about the insights that we learn from running this analysis, and then I'm going to talk about some of the obstacles that we're facing when dealing with FIPS 140 related data, and how we did manage to overcome these obstacles in the case of common criteria, and where we're failing so far with FIPS, and what changes would be required, and how it would help the whole ecosystem, in my opinion. By the way, our tool also comes with a fairly comprehensive Python API for the power users. So we update the results weekly, so the people can just download our data set. If they want, they can also turn it into some tabular representation. Maybe they want to limit their attention to certificates released in the last 3 years. Maybe they want to take a look at only 140-3 certified modules. And they can then just run some statistics, see how many certs they are facing, and compute anything on that. So this is for just some analysis that you can do with our tool. So how do we actually obtain the whole data set? So we first start by crawling the NIST website, and we download all the HTML files for the modules, and we also download the PDFs of the security policies. And then we just convert them to some text representation, from which we then extract attributes using regular expressions, but we are now experimenting with natural language processing, with large language models. And once the features are extracted, we're facing two difficult tasks that are at the center of our attention. Basically, the first task is we want to link the list of certified modules with a database of vulnerabilities. So we want to see whether the certified modules are suffering maybe from fewer or from different kind of vulnerabilities than the non-certified alternatives. And the second thing we want to do is we want to build a reference graph. So something like a dependency graph between the certified modules. We want to see how the modules are relying on each other, because this gives a lot of insight. I'll talk about it a bit later. And these tasks highlighted in the red area are fairly difficult, and they are stochastic in nature, and so there is some error to that, and we have fairly high error rates when it comes to dealing this in FIPS 140, and we figured them out fairly nicely when it comes to common criteria. So hopefully now we're on the same page, understanding that there are some interesting metadata hidden in the certification artifacts, and I wanted to give you a brief showcase of some of the insights that we've learned by analyzing these artifacts. I will keep it really elementary here. As I said, I will not be drawing any strong conclusions because I'm not an expert into the certification, so I will keep that to you. So first of all, you can take a look at just a few lines of code, and you can plot what's the number of modules certified under different standards. This little thing over here is 140-3, so the newest standard. The situation is, of course, changing every day. This data set comes from the August, so it doesn't really cover the spike of the interim certificates. The plot could be different if I plotted that just today. But yes, you can see that the FIPS 140-2 is still the most prevailing as of today. You can also observe how the different module types are popular. You can see that the software module types are gaining traction, and by now are as popular as the hardware module types. When it comes to different embodiments, you can see that the multi-chip standalone is the most popular by far. And you can also see that this is a thing that doesn't change throughout time, really. Security level-wise, we see a large number of the level 1 certificates being issued lately, which drags down the kind of statistics of the average security level. But again, this is not by not having the large number of high security level certificates, but rather by having a really, really large number of low-level certified modules. And I also know that there is some tension in the community when it comes to the queue, to the processing queue of FIPS, how long it takes to receive a certificate. So you can also measure the certification progress, because NIST releases 2 lists that cover implementations that are currently under test and modules in process. And they basically release on a website the list of modules that are and how they are undergoing through the different stages of certification. So you can observe where the bottleneck may be, how long does it take, how long does it take in the older standard compared to the new standard, and so on. So what I'm showing you right now is a cumulative distributive function. The green one is the older standard, and the higher the curve is, the better it is, actually. So the shorter time the modules spent under test. And you can see that for 50% modules, we're looking at more than 9 months, pretty much. And there seems to be some strict cutoff after 18 months of time, when the modules just leave the list no matter what. We're collecting the data for 4 years at the moment, and I believe that they are being updated weekly. So another thing that you may want to take a look at is how much time do the certificates or the modules spend in the individual stages, and how does the old standard compare to the new one. From this point, you can really see that the bottleneck seems to be the 140-3 in review phase, where the modules spend a lot of time, especially compared to the older 140-2 standard. But again, I'm not here to interpret this data really. I believe there was some presentation in the morning that provided update on that, and there is supposed to be some presentation in the next days. That's called making sense of this queue. So now I would like to spend some time discussing the things that I consider really important for our work. We call it future work. We could also call it things that we're currently failing at as a team. And the first problem is, how do you match the list of certified modules to vulnerabilities that in the past affected these modules? This is really interesting because you learn a lot about the ecosystem. You learn maybe there are some attack vectors that do not really affect certified modules. Maybe there are some attack vectors that we should be more concerned about as a community. In order to create such a mapping, you have to be able to cross-correlate these two databases pretty much. So every vulnerability is assigned by NIST with a list of configurations that are affected by the vulnerability in the form of so-called CPE, Common Platform Enumeration. So if you take, for example, the TPM fail, another side channel attack, this chip was vulnerable in combination with any of these firmwares. Okay, so there were 2 firmware versions that were vulnerable to this flaw, and the CPE is basically a data structure that says this is the chip name, this would be the vendor name, and there would be also some version sometimes. So the idea would be try to go through a list of certified modules and try to find this thing right there. The problem is, yes, there exists a FIPS module of this chip, so it could be vulnerable, but somewhere in the security policy in the PDF file or somewhere hidden on the HTML of the module, you can find out that the firmware version used in this module is different. So you do not have a clear match. But what I want to say is, if the certified modules would be issued with common platform enumeration records when they are issued, this will solve the problem completely, and you will have very clear mapping to the vulnerability database. So you could watch out for And you could take a look at which vulnerabilities tend to affect the certified devices. So in common criteria, it's not that ambiguous. We typically are able to extract the CPEs from the certificate name, but we're not able to do so in FIPS because the information is much more dispersed. It's not conveyed in the module title, but the firmware version is hidden somewhere on the HTML or in the PDF file. Another thing you could do is you could hunt for exploitable misconfigurations. We all know that cryptography is notoriously difficult to get right when it comes to configuring the primitives correctly. So a misconfiguration could actually lead to exploitable vulnerability. And the configuration is often communicated by the security policy document. So like 6 years back, these 3 people actually examined legacy RNG implementations. And they, we will talk here for a second about X931 RNG. It uses AES as some underlying cipher, and the cipher uses some key. The inherent attribute of this pseudo-random number generator is that if the key is known to the attacker, he can predict the outputs of the random number generator. It's not a flaw, it's just an inherent like design feature, okay? So in history, this algorithm was actually approved in a FIPS, and the FIPS specification did not say how to handle the key K, the secret key. So the authors of this paper actually went through all the security policies that were relevant, that talked about this, this algorithm, and tried to figure out whether there was some certified module that mishandled the key. In fact, there were some modules that were mishandling the key, but now we live in 2024, right? You could just ask ChatGPT. So you could throw the security policy document at ChatGPT and ask, does this cryptographic module include this pseudo-random number generator? And the answer would be yes. Then you could ask, okay, so what's the underlying cryptographic primitive? It would say, now we're talking about triple des. And then you can ask, how is the secret key for the underlying triple des instance generated and handled by the module? And this is when it gets this is when it gets interesting, because the response, and the response is correct, by the way, is that the seed key is generating during the manufacturing process and stored securely within the module. So wait a minute, does it mean that the key is really hard-coded there so that it doesn't change? Can it be that the whole key is like, there is a single key for the whole production line? It turns out that the key is, there's a single key for the lifetime of a product, but it's not shared between the different product instances. But once you actually recover the key, you can just predict the outputs of the RNG. And so my idea here would be that the security policy documents, they talk a lot about how the cryptographic primitives are configured, and so you can automatically search them for these misconfigurations these days. Another thing that you want to do is to build a reference graph. The dependency networks have been thoroughly studied in the world of software packages, and we also investigated the dependency network in common criteria. And the primary motivation is that when you have a certified module that is used as a dependency in another certified module, and when the vulnerability gets discovered in one of them, it may translate to the other one, right? So you want to know about this edge, especially when you're assessing the impact of vulnerabilities. So let's take a look at a single certificate. This is some Cisco wireless controller, I believe. And on the HTML file, you can actually find that this module is uses this ACT2 Lite certified module as its underlying component, pretty much. It's okay. You can search all these modules. You can try to connect the dots, and you will figure out that the ACT2 Lite components is actually a pretty important one. There are like 20 different modules that use it as its dependency. The green ones are those that are active. The yellow ones are those that are sunset at the moment. And So as such, the module right in the middle constitutes an important target for the adversary, because when you break it, there are chances that you break all these things as well. And it constitutes an important asset for vendors as well. And this graph is super interesting for us when we're doing the vulnerability impact assessment, because had we know that we have broken this thing, we know that we have to watch out also for all the other neighbors in the graph. Well, the problem is, how do you construct this graph? So each FIPS certificate is issued with some identifier, but this identifier is terribly ambiguous. It's just a number, okay? And they are numbered from 1 to, I don't know, 4,700 these days, I think. So there's a lot of ambiguity, because you can find some random numbers in the policy document, and they could be meaningless. They could be unrelated to the actual identifier. In common criteria, we have unambiguous identifiers, pretty long, something like a magic number that cannot be mistaken. And from these, we were able to reconstruct the full graph, but we're failing to do so in FIPS. And so I just want to give you appreciate the whole picture of how the reference graph roughly looks like when we construct it from FIPS. But beware, there are some extra edges. They are not supposed to be there due to the ambiguity, and we probably miss some other edges. But we can see that most of the certified modules are isolated. They're stand on their own. They have no certified dependencies. They certainly have some dependencies, but these are not certified on their own. But we do see some rings, some that I have shown you, where there are many certified modules relying on the security of just one underlying thing. So these would be like critical components in the system that make it slightly more fragile. So I wanted to give a series of steps that I believe would benefit the whole FIPS 140 ecosystem, that would make it more easily machine processable and my life more easier when I'm collecting this data. So first, I want to appreciate that there are some efforts to automate the cryptographic module validation program. But I also believe that the NIST or vendors should assign some robust identifiers when they are issuing the certified modules. I also believe that these should be assigned with the common platform enumeration records. So this would simplify linking to the vulnerability databases. I would also love the PDFs to be replaced with something that's more machine processable by XML, for example. But that's just my personal preference. I'm not having any strong opinions in that. And I also believe that the software bill of materials should be promoted. I believe that this is happening, and this has been adopted by NIAP as a policy for common criteria certificates. But unfortunately, NIAP actually keeps these bombs for themselves. They don't make them public. So again, I can't really access them, so I can't see how it impacts the whole ecosystem. And also, the NIST website is in a sense very fragile, because once something gets deleted from there, it's deleted forever, and you can't access it anymore. So it'd be very nice to have some snapshots archived over time. So to summarize my talk, I wanted to communicate that monitoring the certification artifacts brings more transparency and visibility into the ecosystem. I believe it's a valuable effort. However, any deep analysis, I give just some hints, is thwarted by a lack of structure. We're facing free-form data, but maybe when the artifacts were predominantly written to be consumed with an idea that they're going to be consumed by human beings, maybe we could tackle them with natural language processing these days. But if we introduce some structure, that would be also nice. The SecCert tool was conceived to aid the vulnerability impact assessment, and I like that it's being adopted slowly in the environment exactly for this purpose. We weekly update our results. We collect the data set every week, scrape all the certified artifacts, convert them to text, extract the features, and release the updates. So it's all available from our website. And if you wanted to follow up, then definitely speak to me. Tell us if we're wrong, because we may be wrong, and we have just little insights into the certification landscape. And if there are any feature requests, if you just go through the web, you can definitely mail us if there's something that you miss and you would like to see there. So I think that would be it from me. And now you must have some questions, so ready to answer them. Yes, thank you.
Questions, we have 5 minutes for questions.
So thank you very much. I think very important and very good work. So thank you very much for doing it. You say the sort of motivation started with the Roker attack. If you sort of went back in time and looked at the sort of certificates that were around that covered some of the Roker vulnerable devices, would you have been able to uncover the sort of full extent of the damage that Roker had done, do you think?
Oh yes, absolutely. At that time in 2017, my colleagues didn't really take a look at the certified devices at all, pretty much. But then we ran some initial assessment and we figured out that there is like 10 common criteria certified devices affected. But then we ran a thorough assessment with help of sectors, and we figured out there is like 50 more, and there are pretty dense components in the graph, some like transitive references, pretty much. Devices where we cannot immediately say they were impacted, but they might have been, or they might be. So it doesn't fully automate the assessment. It just guides you and steers you as an analyst. So that's it. Thank you.
I have 2 questions.
Uh-huh.
The first is for the MIP stages that you had for FIPS 140-2,
Yeah.
that slide.
Yeah, I can go.
Was there historic data available for you for the 140-2 certificates?
So let me just get back to the slides. Yeah, this thing. So the NIST, as I said, they release snapshots and we collect them over time. So once the data gets deleted from the snapshot, it's not available, but we have collected it in the past. So we have the whole timeline. And then we can just correlate it to the individual modules. So it's publicly available if you keep collecting that over time.
Okay. And with that representation there, how many years are being represented of data collection?
We started collecting that in 2020, so it's last 4 years.
Okay.
And the lists, they are available in JSON, so if you want to download that,
Excellent.
it's all there.
And then my second question, for the artifact set that you're downloading from the site and scraping, does that also include CAVP certificates?
I am actually not certain at the moment. I could double check and get back to you.
Okay. Thank you.
Thank you.
Any more questions? We have 2 more minutes.
Not really a question, but I was curious if you had used like the Wayback Machine to get some of the older FIPS 140-2 data. And if you can download it from that.
We
or
did
if
not,
it's not.
and I'm actually not certain whether, like, to what extent the NIST is indexed, but maybe it could be.
It's on there a good bit. I had to, sometimes CMVP would update the date for when we first went in, and so it was hard to find out how old a module had been in there, but you could go back and find out. But yeah, I don't know if it
Yeah, we just download everything just in case it's not indexed. So, but yeah, this is an alternative to use the Wayback Machine, of course. Thank you.
I have one question for you. Since I'm the moderator, I have the right to give the last one. So based on your study, can you reach a conclusion, or it's still inconclusive, that the validated module performs better, it's more resistant to the vulnerabilities?
So I can't really give any results for FIPS validated modules. I can only talk about common criteria modules. And we see that they tend to suffer from, like, landscape-wise, they tend to suffer from the very same vulnerabilities as open source projects. So it's not like that any attack vector would be eliminated by the certification. We see that the level of certification is negatively associated with the average severity of the vulnerabilities, meaning that if you really certify to higher levels, the devices tend to suffer from less severe vulnerabilities on average. It's not super strong correlation, but it's there.
I see. Well, thank you very much.
Thank you.
Yes, please come on in, find your seat. We are going to introduce our second speaker for this session. I'm very happy to introduce our second speaker, Nicky Mouha, and he's going to share with us his presentation about NIST SP 838 series status update. Status update on the bronze. He has a very impressive resume. Please read the online version of his CV so that I can save some time for him to start his presentation. Let's give a hand to Nicky.
Can you load my slides?
Oh, the slides. So I hope I can find your slides. Sorry. Different tab. If you can help. Thank you very much. You are so well prepared.
This should be it. Perfect.
This one, perfect. So you go the presentation mode.
Yeah. Perfect. Thank you so much, E. My CV is not online, but if you ask me, I can send it to you by email. I'm really happy to be here to make two big announcements that I've already announced earlier this year, but it's going to be the first time to announce at ICMC. NIST will standardize a new block cipher and a new block cipher mode of operation. So that's going to be the topic of this talk. We had organized the third block cipher modes workshop in October of last year. So people were saying, oh, why the third? Well, the first and the second were in the 90s. So back organizing workshops where it was stated in the description of the workshop that NIST is particularly interested in discussing the possibility of standardizing a tweakable white block encryption technique that could support a large range of input lengths, and also to discuss how NIST could best address the limitations of the current block cipher modes of operation. Then the fourth block cipher modes workshop was held this year in June, but it was not called the fourth block cipher modes workshop, it was called the NIST accordion workshop. I have to say in the next slide what actually an accordion is. And what was said there is that the idea was to go standardize two accordion modes. And this would be beyond birthday bound secure accordion mode with the AES block cipher, and then non-beyond birthday bound secure, because it's not necessary when you have a wider block size, for Rheindel 256. This is basically the first part of what I was saying in the beginning. There is plan now to standardize what was already submitted in the 90s to the NIST competition. To the AES competition, Rheindel with 256-bit block size. So in that case, if you look at what birthday-bound attacks are, instead of 2 to the power 128 over 2, it's 2 to the power 256 over 2, so you can process a lot more data and hopefully don't reach any of the restrictions in practice. So this is on the table for NIST, a new standard for a block cipher, and also for a block cipher mode. And the mode is the accordion thing that I will go into in the next slide. Another thing that was announced is that there will be some exploration of other types of algorithms, modes of operation, such as AES, GCM, SIV and its variants, and CAT-check-based AEAD. This talk is about reasoning about requirements. So as we were working internally on the requirements documents related to the NIST modes of operation, I wanted to introduce more engineering into the discussion. So this is my talk that I'm going to give here. Here you can see an overview of different hierarchies in which you can consider different properties if you want to discuss what we're actually trying to do. So you can have on the inner layer a block cipher, possibly a tweakable block cipher, where either like the tweak is included in the block cipher. You have like a tiny mode like XCX or something that is done on top of the block cipher. So then you have a fixed length key coming in, a fixed length tweak coming in, and also the plaintext and ciphertext are fixed to the length of one block for AES 128 bits and for Rindell 256 bits. One layer higher is the mode of operation. The idea of an accordion cipher, I didn't come up with the name, but that's what it is now, is that basically your mode of operation behaves in the same way as your block cipher. So it would mean that you stretch the width of the input to the width of the entire plaintext. But as you're used to with a block cipher, whenever you flip any of the bits of the plaintext, you will see a random ciphertext appearing. Whenever you flip any of the bits of the ciphertext, you'll see a random plaintext appearing upon decryption. That is something that the classical NIST modes of operation don't have. And is also a source of many of the attacks when people see how cryptography being used in practice is going wrong. If you go then one layer higher, if you look when you have this accordion cipher, well, internally in some of the meetings, I was saying white block cipher, but that's confusing. People think, when you mean white block cipher, do you mean twice or 4 times the width of AES, or do you mean the whole plaintext? So accordion is trying to make it clear that it's the whole plaintext, because as the instrument, you can pull it out to the width that you require. So when you want to use that to do, for example, authenticate encryption, key wrapping, disk wrapping, you need to use what NIST calls derived functions. So you need to specify an encoding of how you want to go from the inputs that you're provided on that level to the inputs that you need on a level lower of the accordion cipher. And then whenever we talk about things like, let's say, a tweak, right? You can see a tweak on the highest level, which would be, for example, for disk encryption, the block unit number or the disk unit number that you're encrypting, the sector number. On the accordion cipher level, it would be the tweak that is coming into the cipher. And then on the side of the block cipher, perhaps there's a tweak coming in there as well. Or on different levels, you can look at how a particular parameter appears. So here is the next framework. So this is what I introduced internally to try to have a meaningful discussion about requirements. And the idea is, well, what we're trying to do is not cryptozoology, like trying to see which animals exist in the zoo. We're trying to do crypto engineering. We're trying to see which bridges do we want to try to build. So actually we're reasoning not about any existing mode of operation or any existing cryptographic construction. What we're doing is we are reasoning about any possible way in which you might design a cryptographic algorithm or a cryptographic mode of operation in this case. So that makes it slightly more complex because you need to explore more ways of doing designs. But there are some patterns that you will see when you look at how people have done designs and what are the ways in which you could reason about requirements. Next, NECST is trying to capture every possible way of reasoning about a requirement. And whenever you want to have a discussion, perhaps it can be helpful to see how do we fit these few letters, how do they correspond in this context. So N stands for new features or future proofing, which would mean, is there something that the NIST modes of operation are currently not doing, but that you might need in the future that you would like to have as a new feature? E, which is extremely important but overlooked, especially by people who are not so familiar with benchmarking and implementation, is the actual efficiency, performance of the construction. C refers to compatibility, where compatibility is referring to, can it replace an existing standard? So whenever people are interested in having some like drop-in replacement, I already have a standard, I want to use another new standard instead. Does it actually fit there, right? So that's one way in which you can reason about requirements. S for security, so is there a security relevant reason to have a specific or not have a specific requirement? And then to be complete, there needs to be some catch-all category. And also every time there was some thing that you would have as a reason to have a requirement that didn't fit this, Usually people refer to it as a technical reason. I looked up online, what does it mean, technical reason? And the explanation that you find on the first search results are, well, you say something has a technical reason if there is something that doesn't work or can't be done. And basically, once we look at what those technical reasons might be, it starts to become clear, where you might have a thing that fits into the catch-all category, like a technical reason why you may or may not want to have a requirement. Okay, so starting at an observation made by Phil Rogoway, who was invited speaker at our third block cipher modes workshop. He said, well, there are 17 AES-based modes in the NIST series of standardized modes of operation, block cipher modes of operation. And he said, well, if you would like to start from scratch, how many modes would you actually have? And the argument he was saying is, well, maybe you would have just one. And then when people say, well, which one would you want to have? The description that is given is that people would typically say something that acts, a mode that acts as if it were a white block cipher. So from this I can distill two requirements, like one would be C compatibility. A requirement would be if you want to have a drop-in replacement that whenever you have a current application of the NIST SP838 series that have a certain restriction on the inputs of the parameters of the inputs, that whatever thing is allowed there should also be allowed for new mode of operation if you want to be compatible. And then an interesting thing that Phil mentioned and the way that he describes it is, well, you'd like to have something that behaves like a new white block cipher and maybe just one mode of operation. However, there's some types of things that the NIST modes do, like FF1 and FF3 and 38G, that, as Phil described it, may cause a headache. So what FF1 and FF3 allow is to encrypt a credit card number to another credit card number. So it's format preserving encryption. Whatever the format is of your input is preserved as the format of your output. So then you're not encrypting a string of bits, but a string of radix elements, which can be digits, can be alphabetical characters, can be whatever format the input is. And yeah, that causes a bit of a headache to Phil, also to me. So perhaps a technical requirement would be to not necessarily be so general in a new mode of operation that you also want to support string of radix elements. Maybe a string of bits is an easier and more straightforward way of developing a new mode. So here I want to give some higher level description of a few parameters of how an accordion cipher would look like. So it's basically like a block cipher, but wider. There is a tweak that comes in, and the idea of the tweak is that when you talk about authenticated encryption, this is where you would place the nonce, or you place the associated data. But for a nonce, the idea is you're not supposed to reuse it. In the case of an accordion cipher, you want to explicitly make it clear that this construction allows this input, this tweak input, to be reused. What the security implications are on that will be clear on the higher level when you see what that tweak will actually be. This is referred to as tweak, basically selects which block cipher to use. For a different tweak, you're supposed to have a different encryption. There's a minimum input size M and granularity G. So G specifies in which increments you can process the inputs. Another requirement, of course, is that it's invertible because we're trying to construct a mode that behaves like a wider block cipher. Okay, so a question would be like, what would these parameters be? What would be, for example, the minimum inputs, right? If you want to be compatible with the existing NIST series, we can actually look at what the minimum input is that are supported. Here I give an overview of everything in the NIST 38A series. So it can be that, for example, the minimum size is 1 bit. For counter mode OFB and CFV with 1-bit segment, you can encrypt a 1-bit message. So that could be one way of saying if you want to be compatible with this, we do 1-bit inputs as the minimum size. Another could be to say, well, if you want to be compatible with ECB, CBC, or CBC ciphertext stealing, then n bits is okay, because that's the minimum input size there. If you reason about security, then, well, 38G specifies that you would like to have some minimum domain size to protect against guessing attacks, in this case, plaintext guessing attacks. So to avoid that, you can just determine based on the length of the ciphertext what the length of the plaintext is and go over all of the possible, for example, credit card numbers. And then other things in the next framework are these E efficiency and T for technical reason. Well, technical because it's a headache to do format preserving encryption, as Phil explained, and E for efficiency. It's more efficient if you can avoid this FFX style construction that is needed to implement the NIST way of doing format preserving encryption, FF1 and FF3. Another option could be to say, well, maybe the minimum input size needs to be twice the block size. Because if you want to reason about requirements about any possible way of doing a design, it does simplify some designs. For example, AEZ version 5 becomes simpler if you consider that the minimum input size is twice the block size. So these are options and reasonings behind those if you want to design a new block cipher. Then you could say, well, what to do with granularity? Well, granularity would be 1 bit if you look at counter mode OFB, CFB with 1-bit segment, or CBC ciphertext stealing. So for compatibility with those, that would be the requirement. Or you could say, well, for a technical reason, again avoiding headache, maybe we would like to have messages that are an integer number of bytes. We note, by the way, that for the Caesar competition and for the NIST lightweight call for submissions, the requirement stated that the input is required to be byte string. We didn't get any complaints about this, so maybe people are happy just encrypting an integer number of bytes instead of fractional bytes. Or you could say, well, maybe this granularity needs to be larger. There's a security-related reason for this, and I link here to a really interesting paper where you can hide the length of the plaintext better when there's a larger granularity. However, that's not the right way of doing it. The better way of doing it would be to have a secure length hiding padding and provide that on a higher level as an input, not necessarily restrict the length there. Because if you look at compatibility with existing implementations or perhaps new features, for, let's say, the Tor network, you have 509 byte inputs that you want to process with a wide block cipher that has a 509 byte block size. So if you want to support that specific application, you need to have a granularity of 8 bits, not a granularity of the block size, because it's not a multiple of a specific block size. If you look for maximums, then compatibility with the existing NIST modes of operation do not actually specify any limit for CBC, OFB, CFB. There can be a limit for counter mode in practice. For example, for CCM, you can support at most 64 minus 1 bytes of input when you have a really large IV. For security, you will need to stay well below 2 to the power n over 2 blocks. So here I give a link to the Suite 32 attack to show what you actually get a CVE if you use block ciphers like triple DES that have a short block size. And if you want to look at new features, then it could actually be helpful to consider having a wider block size for the underlying block cipher, because then you can avoid limits in practice. Note, by the way, that even for NIST lightweight, there was a minimum on the maximum input size set to 2 to the 50 minus 1. So any submission to the NIST lightweight competition needed to support at least 2 to the 50 minus 1 bytes. To try to avoid it, you reach this limit easily in practice. For efficiency, I should point out that increasing the width of the block cipher is much more efficient than having a mode with a beyond birthday bound security. If you look at key sizes for compatibility and for security, you would like to have 128, 192, and 256-bit key sizes supported. For efficiency, if you care about that, then the fastest one is 128 bits. And then if you want to look at possible new applications, we could say, well, maybe 512 bits. However, in the document that does the review of the advanced encryption standard and tries to see is AES still secure, it's explained there and also reconfirmed there that AES is secure for all of the specified block sizes, all of the specified key lengths, sorry. So it does not seem necessary to explore larger key sizes than the one that NIST is currently recommending for AES. Could look into maybe bit strength, like decoupling key size for bit strength. In the case of the NIST lightweight cipher call, there was a requirement for keys that are 128 bits long, but 112 bits strong, at least. And for efficiency, you could perhaps look into, well, what if I would have a key that is 256 bits of length and 128 bits of strength? So just throwing it out there if you want to look at all possible designs and ways of doing things, right? For tweak size, there are cases where, let's say for 38F, for example, key wrapping, the tweak is empty. So that's one that you would like to support if you want to be compatible with current application of 38F. Here also give the length that is given for the IV of GCM and for FF1. For FF1, it's 0 to max T length, but actually no max T length specified in the document. For security, you'd like to stay, again, well below 2 to the power n over 2 blocks, where n is the block size. Perhaps we'd like to support only byte length inputs here as well. And for new applications, it might be helpful that we avoid reaching any limits in practice, because this is one of the main complaints that NIST is getting about currently deployed modes of operation. They're hitting some of the limits that NIST imposes. For extra requirements, if you want to do things like nonce hiding, length hiding, short tag, releasing unverified plain text secure, misuse resistant authenticated encryption, all those you could handle at the higher level, not the accordion mode itself. But they might have some implications on the accordion cipher. AEAD with key or context commitment, as we saw from the third block cipher modes workshop, turns out to be an important requirement in practice. And perhaps we also may want to look into key-dependent message security, because it was a requirement for 38E for XTS. You could also say, well, maybe inverse free could be explored. In the case of CMAC, GCM, CCM, and FF1, the inverse block cipher is not being used. So this is potentially an additional requirement that you may want to look into to avoid that you need the inverse of the AES block cipher or the inverse of Rindell 256 to 56. I think efficiency is maybe best explained by one slide that shows an assembly dump. So I was really surprised to see what the speed is of Rindell 256 to 56 as I benchmarked it on my old laptop. Here's the code that I was running, and I'll show you in the next slides what the benchmark performance was. So if you look at AES 256, then you have 14 rounds of encryption. So since Sandy Bridge, that means you get 14 rounds, 16 bytes per round, so 0.88 cycles per byte. Since Ice Lake, which is not so recent actually, came out in 2018, you have a 4-time improvement in terms of performance, because you have instructions that can do 4 independent inputs of AES in one white register. So then performance, benchmark those on my laptop as well, goes down to 0.22 cycles per byte, 4 times faster. What would be the speed for Rindell with a 256-bit block size, or maybe a 512-bit block size if we feel really encouraged to make it even wider? Then, well, ideally we get the same as AES, but there is this additional byte shuffle that you need to do. So the number of instructions is double. You need to do a round of encryption, shuffle the bytes, do a round of encryption, shuffle the bytes, and continue like this. As I benchmark the code, what I found is you get 0.25 cycles per byte, which is actually almost nothing slower. So it becomes really interesting to look into considering standardizing this, and this is seriously looking into it. These are speeds in software. If you look in hardware, the operation that you have to rearrange the bytes is just wiring, so you don't have any additional gates that you need to do to support that. And then here, if you want to look at what we want to do with this design, because this is something we'd like to have the community's feedback on, should we either consider Rheindal 256, 256 as it was submitted in the late 90s to the NIST competition, or make some changes? So some changes to look into could be to look into related key attacks, to look into possibly adding a tweak input if that makes the design easier to support a higher level. But we do have to say, well, let's be careful, because if we have a lot of keys and tweaks, I'm giving you numbers here for which the key schedule has already been computed. There is going to be an overhead in the key schedule if you want to support situation where you change the key or the tweak a lot of times. Note, by the way, for efficiency reasons, that whatever new mode of operation that you want to design needs to be a parallel mode of operation to make sure that the bottleneck is going to be the throughput of the AES or Rheindal operation, not the latency, because the latency is never going to be good on any recent or older processor. So I want to conclude here and also discuss some next steps. So the idea is we want to separate the block cipher mode and the block cipher itself. For the block cipher, NIST is interested in standardizing a new block cipher, and this would be Rheindal 256, 256, or some variant thereof, submitted back in the 90s, so I'd really like to have your input on this, and have a provably secure mode, this accordion mode, this tweakable white encryption technique where the width of the input is the width of the plaintext. This is another thing that we're looking into standardizing. I wanted here to give some insights into how we might discuss certain requirements and try to justify them. So I hope this next framework can be helpful to try to have a meaningful discussion about requirements. And I'd like to end my talk here and see if there are any questions. Thank you. Watson.
Yeah, so there's two things that jumped out to me, and one is it seems that you're implicitly treating the tweak that the outermost mode puts in as saying it goes directly into the block cipher rather than possibly getting modified by the accordion mode, but then later on you have some requirements that seem to fight against that.
Yeah, so the idea, I wasn't too clear about that, so thank you for allowing me to clarify. The idea is that on the level of the block cipher, or perhaps tweakable block cipher, that the tweak would be a fixed length input, and that on the level of the mode of operation, that you'd have a variable length tweak. And then on the level of AED, key wrapping or whatever, maybe you have something called tweak, but you will need to specify how that tweak is encoded to a tweak on the lower level. The mode will say how a variable length tweak turns into a tweak that goes into the block cipher. Perhaps you don't need a tweak. Perhaps it's handled already there on that level. So that's the idea. I just wanted to focus whenever we say tweak. Sometimes people get confused. Which box are we at when we say tweak, right? That was the reason for the slide.
And the other thing is, it seems implicit in the structure of your talk that we're building things around a PRP. So we have a fixed size PRP and then we're expanding it to a larger one. But if you look at the security analyses for some of the wide block modes that are used, where they run into the birthday bound is the PRF to PRP jump. If you build on PRF directly, you'll avoid that and get a beyond birthday bound thing. Sometimes, not always.
Sure, so which PRF are you suggesting, right?
Right, that does complicate the standardization issue and the security argument, but it would avoid artificially reducing the security in some cases for some instructions.
So it's an open problem in symmetric key crypto to build PRFs. I'm really interested to know how to do that. But of course, there are some constructions, right? Like XORing two PRPs, but then, okay, you haven't actually saved too much there. Yeah, you're right. Like this is a reason why it makes sense to have a wider block cipher, so we don't hit this this limit. So I fully agree with what you were saying.
Yeah, okay, so we have 1 minute, but if our third speaker is okay eating a little bit into your time, we are not going to accumulate the queue any longer. Finish that 3, okay? You the end, okay? So go ahead.
1 question per person, so think hard.
Okay. If I understand correctly, you want from the accordion mode that change of 1 bit will change almost all the output bits. For example, if I change the 1000 bit, I will get all the results different. Is that correct?
No, so if all of the bits change, that would be a weakness. So we want statistically half of the bits to change.
Okay,
yeah.
but still you want to, at the end you told that you want not to, the latency that not be that the bottleneck. So how do you want to manage that, that the latency won't be the bottleneck in that scenario?
Yes, so the idea of the last slide is to say that the mode of operation should be a mode of operation that invokes the block cipher on different parts of the plain text in parallel, so that you're not slowed down as you are for example, CBC encryption by the mode of operation. However, you will need to wait until you have all your plain text as input provided before you can know even the first block of the ciphertext, because any bit that is different in the very last part of the plain text will impact the first part of the ciphertext.
Yeah, so similarly to sponge constructions.
There are many different sponge
Okay.
constructions, so yeah.
Yeah.
Thanks.
So I'm going to really encourage you move fast a little bit.
Sure. So
Get
we're
your
doing-
questions out. If there's a lengthy discussions, I would encourage you to do the whole way discussion. Okay.
I'm sorry for, yeah.
So I'm just curious about whether other sort of emergent properties of the block cipher modes were considered as design goals. For example, behavior under error correction or transmission in a noisy channel.
No, that's a short answer, yeah.
I'm very interested by the proposal to sort of revisit Rindell 256, 256. This opens up a lot bigger parameter space for text in terms of match plain, match cipher, chosen plain, chosen cipher, and so forth. We've done a lot of cryptanalysis of block ciphers over the past 25 years, boomerang connectivity, linear hulls, bike leak cryptanalysis. None of it's been applied to Rindell. How quickly do you want this done? Because I could write you 10 PhD proposals right now.
I do not decide on timelines. I do want to say that I agree with the general sentiment of what you said, that there is more cryptanalysis needed, and we'd like to have the feedback of the community on this old proposal that is already out there for quite a long time. However, there's nothing, and actually so far we do not know, even in the strongest models, of any attack at all on Rindell 256 to 56, even though there are a few papers on it. So yeah, be interested to look into it. Thank you.
Thank you, Nicky. Okay, so now I will introduce our third speaker. And I think an extra to us, work for your benefits, that we allow more people coming into this room, switch from the other presentation. Our third speaker is Brandon Harvey from Oracle, and he's going to talk about FIPS 140-3 in the cloud, practical strategies from a real-world case study. And please check out his resume on the conference webpage. Let's give a hand to him.
Yeah, I've got it. All right. So thanks everybody for joining me today. I really wanted to share some of our experiences as we've taken some of our modules through FIPS 140-3 validation using our Oracle Cloud infrastructure. And for those of you that have worked with me in the CC context, I'm also the technical editor for the CC in the Cloud technical community. We put out a publication earlier this year that gives a lot of guidance for PP authors that want to extend cloud evaluation methodologies to common criteria. And I'm going to kind of present some of those themes in a FIPS context as well. So let me get started here. So I'm not sure exactly, what the audience's level of familiarity is here for the cloud. So just like as a show of hands, how many of you are working on products that are going to be deployed to a cloud environment? All right, so that's pretty good amount. How many of you are working on products that are designed to be cloud native? Also a pretty good amount here. And how many of you are working on products that are going to be designed to operate in a multi-cloud environment? Okay, great. So I will probably not spend as much time here on the cloud overview, but we do have some folks that aren't as familiar. So the first thing you need to know about cloud is that it's somebody else's computer. So because of that, the responsibility and who's enforcing what security controls is going to vary depending on what you're provisioning from the cloud service provider. So something we use a lot in the common criteria effort is that there's a shared security model. This is pretty well defined. You can find this in the Cloud Security Alliance in depth. But there's generally 3 different cloud topologies that you're going to find among cloud service providers. So you can see infrastructure as a service, platform as a service, software as a service. When you're doing things on-prem, you're responsible for everything. And then as you move up the technology stack, more and more controls are going to be delegated to the cloud service provider. So like if you're getting infrastructure as a service, you're going to get a server. You install the operating system, you're responsible for all the controls above the operating system. If you're going to buy a software as a service offering, you're pretty much just going to identify your users, authenticate them, and bring in data sources there. So when you're doing a cryptographic module evaluation, you're going to need a compute resource to run your module on. And you're going to either provision a virtual machine shape, or you're going to get a bare metal piece of hardware that you're going to install an operating system to. And sort of with the VM, you can, the cloud service provider is going to do that a couple different ways. There's going to be some virtualization layer in their control plane. That could be like a type 1 hypervisor or a type 2 hypervisor. That's kind of like an outdated sort of topology, but essentially there's going to be a guest OS and a host OS. There was a lot of language in the FIPS 140-2 management manual that sort of addressed this. It's kind of gone away in the 140-3 manual. But the key kind of thing here is that the cloud service provider is going to have to do security updates and bug fixes and that kind of thing. So your VM shape that's on top of that virtualization layer is probably going to change, and it's going to be transparent to your virtual machine. So in the context of a FIPS evaluation, that's a little problematic, right? With bare metal, you're getting the server. You're not, if you're targeting a specific operating system for your FIPS evaluation, you don't have to apply those updates. You can keep it static, so your test environment is well defined, right? So that's sort of a primer on what I'm going to be talking about. But how does that relate to FIPS 140-3? So a couple of baseline assumptions we have here is, can we even do cloud testing with 140-3, right? So if you crack open the IG and you look for the word cloud, you're not going to find it. It's not there. I'm not saying that's a bad thing. I think that, I write a lot of standards for common criteria. It's okay to be vague, and it's kind of all right to not prescribe too much and limit people's opportunities. So if you open the management manual and you look at remote testing, you can see that there is a tiny little paragraph there that allows the use of third-party cloud services that a lab can test on, right? And so they mentioned like AWS and Azure and that kind of thing. But I'll touch on that more in a minute. And so when we were looking at common criteria in the cloud, we had these same sort of assumptions that we're working backwards from. And a lot of people said, well, like, is it really any different? So if you have a cryptographic module and your product is more of a lift and shift kind of thing to the cloud, it's probably not very different really at all. And that's kind of the first phase with common criteria in the cloud, is these protection profile authors look to embrace the cloud methodologies. If it's kind of a lift and shift effort, all of your assumptions from your operational environment are pretty consistent. So there's really not a wide deviance in what you're either your cryptographic module or your target of evaluation are going to need to do. But if we're talking about a cloud native module, things start to get kind of wonky on us. So the boundary of your cryptographic module might be different if you're talking about something that's cloud native. If it's designed to be very mobile within the cloud, and you need to deprovision your module and reprovision it and move across high availability domains, that's something that we're probably going to struggle with FIPS 140-3. And then if you're doing key management and you're relying on like a KMS in the cloud or an HMS, that's also going to be, I think, pretty problematic with the current guidelines. So yeah, to look at the actual remote testing requirements that we're leveraging so far, I have a screenshot from the management manual. And the main takeaway here is that CMVP wants the FIPS lab to have enough control of the test environment that they can satisfy their NVLab accreditation, and that they are confident enough that they can have trustworthy and repeatable results. So that's sort of the main thing. But then the second portion of this is that your operational environment needs to be well defined, right? And let's see if I can read here. So yeah, you have to have an operational environment that includes a specific OS version, a hardware platform version, and a processor, as well as the microprocessor version, as shown on your module certificate and security policy. And then obviously that's going to be present in your CAV certificates. And the lab has to be able to verify all of that information. So like I said earlier, if you have a virtual machine, you're not necessarily able to confirm the underlying control plane layer. So really what we're getting into here is that if you're going to do FIPS 143 in the cloud, you're going to have to test on a bare metal platform. And I'll touch more on that shortly. But before I do that, taking a look at some of the existing OEs that I've pulled off of CAV certs. So these are presumably products that are operating in the cloud. So an OE here, we have Amazon Linux 2 on an EC2 bare metal shape, which is using an Amazon Graviton 3 processor. That doesn't really have a whole lot of specific versioning information there. To look at another example, we have Azure Host OS on a specific CPU, with the PAI or PAA information, and then it's on a Dell PowerEdge R840. And then this next example is kind of like more what you would see in a cloud environment. And we have a Google prod image with Linux, presuming the kernel 5.10.0 on an AMD EPYC processor. And then finally, we can see here we've got Oracle Linux 9 on KVM hypervisor, which is running on Oracle Linux 8, and that's on a specific AMD processor. So like, what can we take away from that? Well-defined isn't very well-defined at all. And that's kind of problematic because, we can't really trace back between cloud vendors what's really kind of being tested. And for the end users of our cryptographic modules, if you show them a FIPS cert and you say, yeah, we tested on our cloud platform, you can go and provision it this way, and this is a configuration we're going to deliver to you. They don't really have a lot of confidence that what they're getting is what was tested. And like I said earlier, we're locked into bare metal testing here, and that's really cost prohibitive. If you're looking at provisioning a bare metal server from a commercial cloud provider, the rate is typically measured in the dollars per hour range, or the double digits of dollars per hour. Whereas if you're provisioning a virtual machine, it can be cents per hour, often a fraction of a cent per hour. So it's literally hundreds, thousands of times more expensive to do this on bare metal, because the hardware configuration that you're getting from the cloud service provider is designed to accommodate hundreds of other customers. So they have terabytes of RAM, they have multiple processors, really expensive kind of resources, and you're reserving all of that for your personal use case. And when you're doing your FIPS validation, you're wasting millions of clock cycles, just kind of like having that sitting there, right? So it's very cost prohibitive. If you're a hyperscaler and you got a good deal on your internal cloud hosting leases, then that's one thing. But if you're a vendor that is not a cloud provider, but you want to deliver modules that your customers are going to use in a cloud context, it's kind of prohibitive. I mean, FIPS isn't really cheap to go do in the first place. So if you add on, tens of thousands of dollars or hundreds of thousands of dollars because you have a whole bunch of different OEs that you need to test on a cloud environment, we're locking people out, right? So, and it's also prohibiting the labs from offering cloud-based test infrastructure to their customers if they wanted to take some of that complexity away. The bigger the sandbox, the better the castles. So it's something we should probably address. What should it look like? We could capture some very easy information in our ACTVS certificates. So kind of starting, we could capture the cloud provider, first of all, the region that the OE is being tested in. Not all the time is that super relevant for cryptographic operations, but it would help the end users to know that the module that they're getting is what was tested, especially if there's like data sovereignty concerns, and they know that their region has been validated. The VM shape would be very important to capture if we were going to move in a direction that allowed virtual machine testing. Obviously, the bare metal specifications are very important to capture. If you're talking about a module that's just going to live in a container, that's a whole different set of information that you probably want to capture. Sort of the orchestration mechanics behind the container are important to capture. I think it'd be kind of neat if we had like a YAML in a security policy, so your customer could just pick up the YAML and go run, and not have any type of extra things to go set a FIPS mode and go do these other things. It would also be really interesting. I know that I've been told that there have been a couple of 140-3 modules that were done as source code only, which is interesting if you're talking about a serverless implementation. So if you could just take your source code and present it to AWS Lambda, and now you've got a FIPS validated module there. That's kind of a paradigm shift, and I don't know if we'll get there, but I think it's interesting to think about. So now that I've kind of gotten that out of the way, I'll share with you some of our experience with setting up test infrastructure for 140-3 validations. So to get started, you're going to go to a cloud vendor and you're going to need some space. So you'll get an account, or I think it's generally referred to as a tenancy. So you've got this space, you're working with your FIPS lab, you're going to need to put some controls in place so that not only can you allow the lab to come in and operate, but you'll also going to give them some controls so that they have enough confidence that they're in control of the test environment and they can produce trustworthy results. So one of the things that's available across multiple cloud service providers is isolation mechanisms. So with Azure and AWS, I believe they're called resource groups. With OCI, we have a concept called a compartment, which is essentially the same thing. So on the right here, I have a tenancy that I've carved up into multiple compartments. So I can have isolation around all my FIPS evaluations are over here, my common criteria evaluations are over here, and then I can have subcompartments so that maybe I'm working with different FIPS labs. They're not going to step on each other's toes. I can provision different administrators. They can provision different resources. So you have to think about how you're going to do this. But there's enough capability here that it can be done, and it can be done in a high assurance way. And there's a lot of different variability between the competency of cloud administrators at labs. So some are going to be very comfortable if you just give them sort of an account with capabilities to provision compute or network rules. So they can go in there and it's a sandbox and they can build everything. Others are not as comfortable. So maybe you provision everything for them, but you don't want the opportunity for you to log in and maybe modify something. So you could get their public SSH key, provision an operating system with that, and then they can SSH in with their private key, but you can't get in because you don't have their private key. So that's something that we've used with our lab partners, and I think the specifically this instance with the Canadian government, and they're very happy with that. So obviously I've stressed that this is pretty expensive to do. You can sort of make an attempt to control some of these costs. And I live in Texas, it's pretty hot most of the time. So if we're going to go on vacation, we're going to make sure our air conditioner doesn't run if we're not there. And same kind of principle applies here. You can use different automation techniques to make sure that the resources that you need are only there when you actually need them, and they're not just idling away, costing you lots of money. There's a multiple frameworks that you can operate with. So Chef, Puppet, Ansible, Terraform, CloudForm, those are all sort of infrastructure as a service offerings, infrastructure as code that you can check in, and your cloud provider will spin up or down resources as needed. Like OCI has a cloud API. It's written in a Python library. So you can write a Python script to go and provision a compute resource, to put your cryptographic module on it, to SSH into it, to perform a test payload, and then deprovision all of those things. So it's pretty interesting. And I think that as we embrace more automation in FIPS, that this could be something that, well, I'm not sure if NIST would like for us to like get CAV certificates for all of our nightly builds. They probably wouldn't like that. But I think it's very interesting that, you know, we're getting closer to a continuous integration, like continuous certification sort of possibility. But there are some pitfalls, right? So if you have existing tooling that you're using on-prem, it's not always going to be directly portable to cloud. So your harness work, you might have some harness work cut out for you for IPsec testing, depending on how you do your tenancy setup. You may or may not be able to do the IPsec tunneling that you need to do to observe. It's a lot more problematic in common criteria because we're doing a lot more negative testing. So like we're doing a lot of man-in-the-middle stuff and stomping on packets and things that you would traditionally do down at the data layer, you're not going to have access to in the cloud. So you need to move your attack vector up to like the application layer and stomp on it that way to get the right results. But yeah, speaking more broadly as to like what would FIPS need to do to accommodate more cloud evaluations, this is kind of my wish list. We kind of need to talk more about jitter entropy. So I have on the right here, I don't know if I see Stefan in the audience. Okay, good. So he's not going to be able to correct me here. So you know, on the right here, we have like the traditional cryptographic model that everybody's familiar with. You've got an application, it's calling a library. That library is going to go to devrandom, and devrandom is going to go down to RDSeed. If we're talking about the modules that are going to be highly portable in the cloud, and you want to decouple your hardware dependencies, so you take jitter entropy, you use the userland implementation, and you're not going to use cryptographic offload or acceleration, so you're keeping everything as tightly as you can in your application. So you put it in a container, you put your application in there, you put your cryptographic module in there. That crypto module is going to use probably the get time syscall, and that syscall, yeah, it is going to go through the kernel. There is like some pass through that happens there, but for the most part, you're going to get the raw timestamp data that you need from the CPU, and there's really not like a lot of variation, or really any at all, between the CPUs that you're going to be running on. And this brings us a lot closer to how cloud native things are happening. So this is far closer to like real world application. We kind of need to decouple FIPS from like looking at a specific CPU if the security functionality isn't really tied to it. And I'm assuming here that this is like an SP 853 B or C compliant module, so it's doing good entropy assessment, and it's got some other guardrails around it. So the quantity of the entropy may be slightly different depending on the cloud stack, but it should be enough quality entropy that we can still have good key generation. So we need like a little more help from CMVP around jitter entropy and sort of decoupling our straight traceability to a given CPU microarchitecture, because it's not as relevant in cloud contexts. There's a whole other series of things that are uncomfortable to ask when you're talking about doing cloud native FIPS 140-3 evaluations, and I think that has to be like a much broader conversation. So mimicking an effort like CC in the cloud for FIPS is probably a good idea. I would like to sort of bring that up. I don't know if the CMUF would probably be the avenue for that, but start talking about that. If you're doing something with the cloud module and there's underlying hardware that maybe the cloud service provider controls and you don't have any access to, how do we work that in the program? Hardware security modules are probably more and more part of cloud workloads because of confidential computing needs. So how do you kind of address that? It's something that we need to work out. And then how does this play into larger automation efforts? If we can get closer to continuous certification, that would be great. And yeah, so just a quick recap, like FIPS 140-3 is cloudy. It's possible, but it's rather limited. It's very costly and it's overly complex. And we need some better guidance and some better rules to make this more feasible and more attractive for module vendors and end users. So that is my presentation. I will happily take questions now.
Five more minutes for questions. I will start one.
Sure.
We will certainly welcome you to reach out to CMUF and we can initiate a working group on this topic. A while ago, I have a co-chair for a working group. It's called Module in the Cloud. And it was before CC in the Cloud. We did a presentation at ICMC, I think before COVID time. And we really hit roadblocking issues because when it comes to cryptography, the algorithms, the entropies, in theory, we cannot decouple from the hardware. Very often, it is a difference in the CPU that give you maybe slightly different behavior of the algorithm, even though the code is identical.
Right.
But it runs on the different architecture of the processor, it may give you different results. So back then, we have the CMEP people participate, and we just couldn't really wave the hands and say it's not a problem, and we can bypass it. I think the agreement back then was that, one solution we can think about is if you look under the hood of the cloud, roll up the curtains, there's hardware behind. If you can test on every hardware platforms that cloud may use, it's invisible to the end users. But if you give all the variety of the hardware gets tested, then you can claim it's okay.
Right.
Yeah, still have to be grounded on that hardware level.
Yeah, we have like a similar set of assumptions that we kind of work with CC in the cloud. So there's a construction that we have there, the trusted platform, because in common criteria, there's no, like, you can't go get your entire cloud service certified under common criteria. You could get like components of it certified, but there are cloud authorization schemes like FedRAMP where they will, consider the entire cloud offering. So we kind of put some guidelines out for using other cloud authorization schemes and tying that to some of the security objectives of a TOE. I think maybe there's like a possibility for composability with FIPS, where maybe a cloud service provider gets their infrastructure validated and then a module could inherit those certifications. But yeah, like truly decoupling from the hardware is very difficult, right? Which, like, I'm optimistic that maybe jitter entropy, if it's only in user land, that maybe that could maybe not be a solution, but maybe we could put some language around that it would make it sort of feasible. Yeah.
Yeah, we can certainly continue the discussion, and everyone welcome to maybe you start a working group, and we have the monthly CMUF meetings.
Yeah.
We can learn from CC in the cloud, your experience, what you get. Yeah. Any questions from our audience or comments? No. So let's thank to our last speaker.